All right, next is multiplication. So multiplication is really a geometric construction. So you start with two numbers, and these numbers are in polar form. So let's say the first one is the number z, where the polar form is the absolute value of z with the argument alpha. So we have z is equal to the absolute value of z cos of alpha plus I sine of alpha. And say the second one, w, is the absolute value of w times cos of beta plus I sine of beta. How do you multiply two complex numbers? So the idea here is that if the first number is absolute value of z units away from the origin and w is absolute value of w units away from the origin, then the product will be absolute value of z times absolute value of w units away. So if you have two numbers and the first one is 2 units away and the other one is 3 units away, when you take the product, it will be 6 units away. So you just multiply the distances. And what about the arguments? So for the arguments, what you do is you add them up. So if you have beta and alpha, alpha plus beta is going to be the new argument. And I think the best way to illustrate that is with a picture. Of course, if one of the two numbers is 0, the product is 0, so that's just trivial. So here's a visual representation of that idea. So suppose here z is this number, and here I made on purpose a picture where it looks like z is like 2 units away. So you see here 2 units away, and meanwhile I have w, which is like 1, 2, 3 units away. So the number that I'm looking for will be 2 times 3 units away, which is 6. But of course, if you are thinking about numbers which are 6 units away, this will give you, of course, a circle of radius 6. And there's a lot of numbers that are 6 units away from the origin. So you need to specify on that on that circle of radius 6 which point is the product. So the trick is the following. So suppose I have my first argument, which is alpha for z and beta for w. What you do is you just add to beta the angle alpha, and the new angle phi for that product is simply the sum of the two. So here the complex number that you're looking for is 1, 2, 3, 4, 5, 6 units away with an angle of alpha plus beta. So there's only one point that will give you a number that is 6 units away with an angle of alpha plus beta. So when you look at the polar form, you see that okay, the distances will multiply, but the arguments were added up. So it's really a geometric construction. We could really do product of 2 points in the Cartesian plane, and you could just have to use a ruler and a protractor where you measure the first distance of the first point, and then you measure the second distance of the second point. You multiply, and then with your protractor you measure the angle of the first one and then the angle of the second one, and then you just add them up for your product, and then with your ruler and your protractor you draw that point that corresponds to the product of the distances with the angle being the sum of the two original argument. So it's really a geometric construction. So let's do an example. Let's take the product. Let's compute the product of 2 plus I times 3 plus I and show that it's going to be 5 plus 5I. So first, if you start with the number 2 plus I, so the number 2 plus I, which is here, what I need to do is I need to compute first how far away it is from the origin. So of course I have a right triangle. The base is 2, the height is 1. So if you go 2 squared plus 1 squared, so the distance of the first number is the square root of 4 plus 1, which is root of 5. What about the argument? Well, because the argument here in blue, I can use the tan, so we know that tan theta or tan alpha is going to be opposite side, which is 1 over 2. So if you're looking for alpha, well, it's going to be arctan of 1 over 2. So you get arctan of 1 over 2 for the argument of the first one. What about the second one? So the second one here, So if you want to compute how far is 3 plus I from the origin, so I have a right triangle where the base is 3, the height is 1. So if I use Pythagoras theorem, 3 squared plus 1 squared is 10. So root of 10 is your distance. About the argument, well, we know tan of beta, so the opposite side is 1. The adjacent side is 3. So arctan of 1/3, arctan of 1/3 is going to be your arctan of 1/3 is going to be the argument for your second point. So if you want just to see it here, arctan of 1/2, I've done the computation for you. Arctan of 1/2 is like in degrees, so it's like 26.6 degrees, and arctan of 1/3 is close to 18.4 degrees. So the polar form of those two numbers, which we don't really need because we want to compute the product, but just as an exercise here. So we have root of 5, so that's the absolute value of 2 plus I times cos of arctan of 1/2 plus I sine tan of 1/2. And then for 3 plus I, I have the absolute value, which is root 10 times cos of arctan of 1/3 plus I sine of arctan of 1/3. So those are the polar form. And now, how do you create the polar form of your product? So we have 2 plus I multiplying 3 plus I. So first, you multiply the distances, so root of 5 times root of 10, and this will give you, of course, root of 50. And now for the arguments, you have cos of arctan of 1/2 plus cos of arctan of 1/3. And by the way, if you're summing up these two angles, this is going to give you 45 degree or pi over 4. So this part here, pi over 4. So the polar form, and this is what's beautiful with this multiplication, is that the polar form is very straightforward. So you take the product of root 5 and root 10, you get root of 50. You add up arctan of 1/2 plus arctan of 1/3. You can use a calculator here, and you're going to get pi over 4. So you get the polar form very quickly. And now if you want to get back the Cartesian form, the only thing you have to do is just distribute this root of 50. So if you multiply root of 50 times cos of pi over 4, it will give you 5. So do that as an exercise. And if you multiply root of 50 with sine of pi over 4, you will get again a 5. So your Cartesian form of your product is 5 plus 5i. So just to recap, if you take the product of two complex numbers and you're going through the geometric process, so you compute the absolute values, how far away the absolute values, how far away they are from the origin, the arguments, so the angle between the positive side of the real axis and the line segment that links these complex numbers to the origin. And then to get the polar form of your product, you multiply the distances, so the absolute values, and you sum up the arguments. And then if you need the Cartesian form, you just distribute the freshly computed absolute value inside your cos and your sine, and then you will get the Cartesian form of your product. But this process is truly a geometric construction. But even if this is a geometric construction, there's, of course, an algebraic way of doing it. And here with the next example, I will show you what happens if you multiply I by itself. And this will give you, of course, -1. So for some of you, you might have learned that I squared, or I is a number such that I squared is -1. For us, it's not the case. It's actually a result that you get through the geometric construction of multiplication. So let's show together that I squared is -1. So, oseka. So, oseka is coming from another language. So, sorry. So we know that the polar form for I is 1 times cos of pi over 2 plus I sine of pi over 2. So because we know that I is 1 unit away from the origin with an argument of 90 degree. So we have the polar form of I that we can just identify in the complex plane. So what happens when you're multiplying I squared? Well, I squared is just a product of I times itself. So if you use the geometric definition of the product, you need to multiply the distances. So the absolute value of I squared will be 1 times 1. And then what about the argument? Well, you need to add up. So pi over 2 plus pi over 2, which will give you pi, of course. So here the argument of your product is pi. So we're looking for a number that is 1 unit away from the origin with an argument of pi. Well, if you move by the argument, by the angle of pi first, and then you go 1 unit away, well, you will land on -1. So the polar form, the complex number with the polar form 1 times cos of pi plus I sine of pi is -1. So here, the product of I by itself will give you -1. So it's really a result. But we can now use this algebraically if you want to multiply two complex numbers. If you just use the regular foiling method, so if you have like two complex numbers and you see them as algebraic expression and you foil every time that you see an I squared because you know it's going to be -1, you will be able to simplify the product greatly. So even if this complex multiplication is defined as a geometric process, we can see that there's an algebraic way to do this algebraic process. And this is, to me, one of the most amazing things with complex multiplication. It's really built on geometry, but then it can be super simplified algebraically. So what we'll do is we'll go over the previous example and recompute that 2 plus I times 3 plus I is 5 plus 5I, but we're going to do it very quickly just by using algebra. So here we go. So suppose we are computing again 2 plus I times 3 plus I. So what I'm going to do here, I'm just going to FOIL. So 2 times 3 gives me my first term. Then 2 times I is going to give me my second term, 2I. Then I multiply I by 3, giving me the 3I. And I multiplied by I gives me my I squared. So 2 times 3, that gives me 6. 2I plus 3I, that will give me 5I. And of course, the sunny moment here, what do we do with I squared? Well, it becomes -1. And then 6 plus -1 is 5 plus 5I. And you're getting your product again. And you can see how fast this is compared to, hey, let's compute the distance and the angle, write the polar form, add everything up for the angle, multiply everything up for the absolute value. Wow, like you can really do this super quickly just by using algebra now. Of course, I'm expecting you to understand both methods, but the goal here is to see that, well, algebraically, this is much more efficient because it does not rely on any measurement of distances and angles.